actually great to come out to this conference. I've been meaning to come for years, and for whatever reason, the schedule has always been a problem. One thing about this talk, I guess before I get started, if people have been following me on Twitter, they realize I had to rewrite this whole talk overnight. And the reason for that is that this might be the only talk that's ever gotten a YouTube takedown notice before it was actually given. And you can say, okay, so let me explain that. Okay, so the topic of the talk, I was going to talk about async, and in preparing the talk, I was thinking, there's got to be some kind of theme, like Star Wars or Mad Max or, some kind of artistic theme to the talk. And unfortunately, my chosen theme for this was Hunter S. Thompson's Fear and Loathing in Las Vegas. So actually, that comment about what was the comment about drinking a second? Okay, so I came up with this talk. It's like fear and awaiting and async. We're going to talk about coroutines, and I was thinking, there's got to be this artistic theme to this. And if you've read the Fear and Loathing in Las Vegas book, which is fantastic, has these insane illustrations by Ralph Steadman in there. There's like this, it's like are they like on a drug trip or something? I was thinking like, well, how could I recreate that? And I started looking around at all of my kids' artwork around the house. I was like, oh, wait a minute, I have this idea, because I have like 6 and 8-year-old kids, right? And I was like, oh, you guys can help me out doing some artwork. So they did a bunch of stuff, and it was unbelievably fantastic. It actually, what it looked like is somebody had played Minecraft for like 12 hours, and then maybe dropped acid, and then went off and did like this art project, and it was like this insane stuff of like flying like ender dragons and withers and like swords and like beasts and all this stuff. It was awesome. I mean, I'm looking at the talk, I'm just thinking, oh, this is perfect for async, But then kind of gets kind of near the road trip day, and then somehow it got brought up. It's like, oh, this talk will be on YouTube, and all of a sudden they're like, YouTube? No way. Like that was it. That was the end of the story. Like, we don't want the artwork on YouTube. So it got shut down. So I can't show you any of the artwork. It was, so kind of leaving, I think there might be a moral, like don't do a project with 8-year-olds. Maybe there might be, and maybe there's some kind of analogy to like Silicon Valley in there or something too. I don't know. Anyway, so what we're going to do in the talk is I want to talk about some of the async stuff that's going on in Python these days. And essentially the story on this is really about concurrency. I mean, it's about having programs that do more than one thing at a time, and kind of the classic, oh, by the way, my only alternative to make this talk just as insane without the artwork is to do the entire talk in the Python REPL. So we're going to attempt that here. So a lot of this async stuff, what people are thinking about are things like servers, network programs, things like that. I'm trying to cut off the bottom of the screen a little bit so it's the people in the back can see. So you might have some code like that. This is like a classic server with sockets, start with that. And essentially the concurrency problem that you run into is just how would you handle multiple clients with this code. As I've typed that in, I mean, I can run this, I can run a server. I can say, well, let's go run an echo server on my machine here, and it will run. That's only going to be able to handle one connection at a time. So if I were to, like fire up like another window here, I don't know if you can see that or not, but let's say you were to fire up a window and try to connect, it's basically echoing stuff back at me. But then if I were to try and do another client, it's going to be stuck, not being able to do anything. I mean, I can type, but it's not getting any response. The reason it's not getting any response is that this first thing is holding the connection open. So kind of a classic problem in concurrency is that sort of thing. Like, how do you handle multiple clients at a time? And there are different ways of doing this. One of the ways that you can do it is to use threads, which I will say, by the way, just as a public service, unless you're implementing the next Facebook or something like that, threads are actually not a bad starting point for a lot of projects. Like if you're doing concurrent programming and you're talking like, maybe hundreds of clients or something like that, I would probably just start with threads. I mean, threads work with most stuff. The programming model is reasonably well understood. Yes, you're going to have to explain to your coworkers about the GIL and other things like that, but for the most part, threads work okay. I will confess that I use threads in production, if it helps. You can quote me on that, and maybe it'll help you out. So threads are one way of doing that. Essentially, the idea is when you get a connection, fire it off into a thread. Another option that you could take is to launch a process instead. Process, what you're doing is launching like an entirely new copy of Python, and then it runs independently. And then you can handle multiple things doing that. One potential advantage with processes is that you can take advantage of more CPU cores if you do that. So if you know about the global interpreter lock and the fact that Python can only run on one core, process is one way around that. The only problem with this is that you're probably not going to run like 10,000 copies of Python on your machine here. So you can do that. A different approach that you can do for this is to start turning to async frameworks like Twisted, Async IO. The issue with that is that you're going to basically be taken into a completely different programming model. If you've worked with these, the general idea is that they have like an event loop sort of running underneath the covers. So you've got this event loop watching the network for incoming packets, incoming things that are happening. And then when something happens, they trigger a callback function. So what ends up happening is you write code where your code is like responding to callbacks. So this is maybe what very simple like twisted code would look like. If you were to run that in Async IO, it maybe looks something like that, where you're receiving connections and responding to events. And this is one way of handling multiple things at once. You structure your whole code as this sort of asynchronous model, and you can handle a lot of things at once. One of the reasons why somebody might do this, by the way, is it tends to be very efficient with resources, especially things like memory, I/O resources, and so forth. If you need to write a program where you've got 20,000 sockets open or something like that, that's why people are turning to some of this async stuff. More efficient than having 20,000 threads running on your machine. So that's why they're doing it. The issue though with this callback stuff though is really the programming model. Programming with callback functions is not the most pleasant thing in the world. How many people have done like callback-based programming? Do you love it? Is it not? Maybe like one hand. Okay, so it's not the most fun thing. I don't like programming in callbacks. And one of the we might as well just see the common slide. It's like there's this kind of notion of callback hell that comes up in like tons and tons of talks. It's like every single talk about async. It's like at some point somebody starts talking about callback hell, and then ways to simplify that. And one of the things that you've actually seen in Python over probably the last 10 years, maybe even longer, are ways of trying to simplify some of this callback programming. Whether you kind of layer different things on top of it, like deferreds or futures, or people playing around with coroutines, inline functions. It's all sorts of just kind of hacks that people have built up. And if you look at a lot of that work, ultimately, what people would really like to have is a programming model that is a lot like thread programming, but not having the resources of threads. They'd have to have an event thing kind of going on underneath, but trying to hide that detail. So really, what the dream would be is to maybe have code that looks like thread, but it's not actually using threads. Now, the code that I've got up here. This is something that is possible in Python 3.5 involving async functions, await statements, asynchronous context manager. You might be looking at this saying, what in the world is this? This is essentially modern Python code using coroutine. We're going to talk about this in a second. I'm actually a little curious before we go further. How many people have played with async await in Python 3? Yeah, only like a handful. Okay, so this is the jumping off point for kind of shattering your head at this point, because we're gonna talk about this. Oh, just to see this work, by the way, I'll go ahead and run this. Okay, so we're gonna just make sure that it works. So I'm in Python 3. I'm gonna run this echo server. Oh no, oh, it's already in use. Okay, well, okay. Okay, so I'm gonna run that, and then let's just make sure that it works here. You can always put it on a different port. Okay. Okay. There's one client. Okay, there's another client. Okay, so you've got two clients connected. Connected on that. Let's shut them all down there. Okay. Testing my iTerm skills here. Okay. Okay. So that's essentially code with coroutines. It looks a lot like thread programming. There are actually no threads involved in that. There's no processes involved in that. But there's this madness with all of a sudden these async functions and things like that. So what I want to talk about for a little bit is actually this notion of an async function. I mean, if there's anything to maybe take away from the conference to shatter the minds of your coworkers or something, I would suggest just dropping this on them. Like you can say, well, you can define like an async function, something like that, and then sort of ask them. It's like, well, what is that? Like, what is that? Like, how does it work? So this is this new feature. First showed up in Python 3.5, defines something known as a coroutine, and it is very different than a normal function. I mean, just to see like the difference. If I write like a normal Python function, like if I say greet name, like that, basically you call that, and it just returns the result back. Okay, it comes back and says hello Guido. If I try to run that async function, like if I say greeting Guido, not much happens. Well, I mean, something happens. It comes back and says, well, you get a coroutine object greeting. And then you can ask, well, what is that? It turns out that these async functions, probably their defining characteristic, if you will, is that they cannot run independently. They will not execute ever on their own. They have to be driven by somebody else. So in order for that function to work, like let's say you say G is equal to Guido there, somebody has to drive it. Okay, somebody has to drive the code. I'll explain that error message in a second there. And the way that these things are driven is you send them a value. Like you would say, well, I'm going to send you a value of none. And then the thing will sort of run, and again, we end up with like an exception. It comes back and says stop iteration. Like, stop iteration? Like, what's that about? Okay, it's like we're not even in a for loop or anything. And then if you look at the exception, it comes back and it says hello Guido. This is odd. Okay, so the function runs, it raises an exception. The value of the exception appears to be the return statement out of the coroutine. Yeah, that's how it runs, actually. Okay, so if you have one of these coroutines, essentially you have to run it, and the process of running it does look a little bit odd. Essentially, what you have to do is you're gonna send in maybe some value. I'll just set it to none for now, and then you're gonna catch like a stop iteration, and then you're going to return the value off the exception. You're looking at that saying, this is crazy, but that's how you run a coroutine, though. So if you have that, if you want to run that greeting thing, that will do it. Okay, so the key thing, coroutines, it's like they don't run on them. They don't run by themselves. You have these async functions, but they're really odd. They're not like normal functions. They're this crazy thing that runs under the context of iteration like that. Let me just pause, make sure everyone's kind of, maybe it's still not late enough in the day for this, but it's okay. So if you've got this crazy thing here. It turns out that there are other things that happen with coroutines as well. if you have one of these coroutines, it can call another coroutine without having to go through this weird iteration thing. Like, let's say I have another async function, like main, for instance. And I want to just, let's say I want to just print out the result of the other one. It turns out that there's this statement, await, that you can use. And essentially what that will do is it will call the other coroutine as if it were just a normal function. So if I were to run main, you would find it come up and say, okay, hello Guido. Somebody's head is like shifting into the projector on that side there. Okay. All right. So that will run it. And it turns out that you can start doing everything that you would normally do with like function calls using these coroutines. Just to see another example, like if I had a function, like this, you could, well, that should have been plural, but I'll do something like that. You can do things like this. You can say, okay, let's do a for loop, and we'll issue a greeting to all of these people. Okay, so you have a function async def. You're using await. We'll go ahead and run that, and you see it kind of calling that other function like a well, the other coroutine like a function. So what you're starting to sort of see here is that there's kind of this whole new world, if you will, starting to kind of open up with async in await. It might look like you've fallen into like a pit or some scary universe, but you have these alternate functions that you can define, these async functions. You have an alternate way of calling these functions with the await. And doing that, you can actually, again, you can do almost everything that you would do with like normal Python functions in this sort of strange, weird world. Just to give you an example of something even more strange, you can do things like recursive Fibonacci numbers with async and await. I don't know why you would do this other than to just annoy your coworkers or something like that, but you could say async def fib, and then it could recursively call itself with like await statements. And I could have like a function that drives that, and this is going to print the first 30 Fibonacci numbers up there. You can run it, and it will crank away on that. Okay, so it just did that code. There was a comment up here about the slowness of this. I've actually timed this. It runs about 2.5 times slower than normal Python function, which is actually faster than I thought that it would do, to be honest. Okay, it is slower, 2.5 times slower. Okay, but the key thing, it's like, okay, can do function stuff, but you have these async functions, you have these await functions. Now, one thing I do have to point out, there is tons of peril associated with everything that is going on here. Okay, so this is a weird universe of things that's going on. First thing, keep in mind that none of this stuff works if you don't run it. Like if I say fib20, doesn't do anything. It just comes back and says coroutine object. You have to run it. If you want to run it, somebody has to drive it. Okay, so anytime one of these coroutines things gets fired, something has to run it. A very common mistake that is possible is that somebody might forget to await it, for instance. That's another way of making it run. Like you could have a function where you do something like print Fibonacci 20, like that. You're violating the rules. You're not actually running the function when you do that. If I run that, you're going to get a weird warning message. Runtime warning, fib was never awaited. Basically, that means you created a coroutine, but you never executed it. Question over here. I guess I could take a question. So.
Does await only, is that only something that can happen in async?
Yes, okay, so the question is, this is an excellent question. Where can you put that await? Okay, so keep in mind, like to fix the problem that I just had, you have to have the await in there. Okay, so that is the solution to the problem is to do that. The mere presence of that, though, raises tons of questions about where can you put that exactly? Like, where can you use the await? One of the places that you cannot use it is you cannot use it at the interactive REPL. The reason for that, by the way, is that the interactive REPL is not running under the management of like coroutines. Like keep in mind these coroutines have to have somebody running it. The REPL is not running under that. And so because of that, you can't await, okay? So you can't do it interactively. You can also not do it in a normal function. Like if I had a function spam and I just said like await fib10 or something like that, that's actually a syntax error. That await keyword isn't even enabled unless you are in an async function. So in order to do anything at all with that await, you have to be in an async function. Okay, that's actually critical about that. Okay, so if you're in an async function, you can use await. You have to spell it right too. Okay, so that is okay. But then you get into these other questions of like, well, where can you use it? I mean, what are the legal places that you can use await? It turns out that you can use it pretty much anywhere that an expression is allowed in Python. I mean, you could, for instance, you could make a dictionary, and you could use it as a key. You could say await fib10. You know. I mean, you could do that. That's okay. Your coworkers might want to stab you or something like that. But you can use it there. I mean, you can use it. You can use it in like arithmetic kinds of things. I mean, it's that's okay. I mean, it's like you can use it pretty much anywhere that a normal expression would be used. I don't know. Let's just print those out and just make sure that I'm not totally full of it here. Okay. Yeah. Okay. So that worked. There are a couple places where it is not allowed. One of the places where it is not allowed, which frankly I find super annoying, because I'm such a huge fan. You cannot use it in a list comprehension. So that is not going to work. You'll actually get a syntax error. I actually almost want to boo that, because like list comprehensions are one of my most favorite features in the whole world, and it's like getting it taken away from me is very painful and cuts deep, so to speak. The other place where you can't use it is in lambdas. Like, so you can't, as far as I know, there's no like asynchronous lambda expression, or you can't await in a lambda. So there are some restrictions where you can't use it. You can't use it outside of async functions. You can't use it in list comprehensions. You can't use it in lambdas. But most other places, though, you can use it. As far as writing code, you can use this async stuff in a lot of different places as well. I mean, it's perfectly fine, like in a class definition, you can have async methods, you can have asynchronous class methods, asynchronous static methods. All of that is fair game. Again, it is a little bit weird though, like if I were to make like a spam object, and then I were to say like, s instance method, it's going to come back as a coroutine, and it's like, keep in mind, that's not going to run unless somebody is either awaiting for it or is going to run it. Okay, so somebody has to run the code. Very, very interesting. Pardon? Oh, that's an excellent. Did I pay you to lead my question? Okay, excellent question. No, this is where things start to get kind of curious. It's like, okay, so if you have these async functions, where can you use those? Like, what are the contexts where you can use it? So you might really anticipate, I have to pay him or something like that. So one question, could you have like an asynchronous init function? Or an asynchronous del function or something like that? In general, the answer is kind of no. And the reason for that is a lot of these, the dunder methods are being triggered by Python kind of automatically because of core features in the language. And those features in the language are not aware of having to run coroutines. Like the fact that these coroutines have to execute on their own causes problems. Like I kind of wonder what would happen here. Like, I mean, we could create a spam and just see what happens. It's really not happy about that at all. I mean, it's like warning messages, and then it's actually giving me a type error because init is returning a coroutine. and it's completely confused about what's happening there. Okay, so in general, special methods not going to work. Although you might, if you, I don't know, take enough drugs or something, start to wonder, like, well, maybe there are places where they could be used. One of the places where it appears that you can get away with using them are on any method that appears to get something. This would include properties, getItem, and getAdder, and various things like that. I'm not going to suggest that this is a good idea, by the way. I mean, it might be a horrible idea, but if you do that, what ends up happening is those attributes become like a waitable attribute. It's like, what do you mean a waitable attribute? It's like if you were to make a spam object, and then you were to say s.value, it comes back as a coroutine because that's what the get function is. It was like a coroutine. If you wanted to actually get the value out of it, you're either going to have to await it or you're going to have to run it. Keep in mind, coroutines never run on their own. So in principle, you could probably do this. I'm not sure it's a great idea, but maybe, I don't know. It's a programming option, let's put it that way. You could certainly make like an asynchronous callable. Classes have this call method that emulates a function call. If you were to make that an async method, you could certainly make that work. There are other sort of more insanely evil things that one could possibly think about. Like, could you use async in a meta class? And not just completely jump, off the deep end this early, but that question that came up, could you have like an asynchronous init method? It turns out that the answer is yes, you can if you're willing to abuse meta classes. What this is doing is it's turning the process of creating instances into an asynchronous operation. And then it becomes this crazy thing where you can actually only create instances through coroutine. There'll be a quiz on this. Later. No, this is nuts. What would happen if you came up here and you said, oh, I want to make a spam object? It would just come back saying, well, it's a coroutine. You have not created the instance yet. The only way that you can create it is you have to run it. Keep in mind, coroutines don't run themselves, so you have to run that. I wonder what other magic is possible. Here are some here's sort of an interesting design space to work in. Do people know about abstract base classes in Python? This is a class where you can make methods that are abstract, and then it will enforce that they exist. Like if you try to create an instance, it'll come back saying, well, you can't do that because you didn't make the right methods. Here's sort of a thought. Is the presence of the async part of the programming interface? Like, let's say you were to inherit from that. Like, I'm going to inherit from spam, and then I'm going to implement the method bar. But I didn't do it as an async. I see somebody cringing over here. Or he's like, probably the right response. No, this is like if you have two different kinds of functions existing in your language, like async functions and normal functions, and then they start to meet up in like inheritance and stuff, this is like where you start to have nightmares, right? It's like, okay, this is insane. So what could happen there? Well, maybe you could build, I don't know, maybe you could use meta classes to do like something with that. You could catch it. You could have it come up and say, no, actually, you screwed up. You need to have that be async. It's kind of odd. We'll see what you think about that there. Okay. The fact that these functions have different rules about where they can be used opens up different other avenues of thought. So here's something I was thinking about. Could you actually detect the context in which a function is called? Here's what I mean. Like, let's say you had a function. Could you determine whether it was being called by a coroutine or whether it was not being called by a coroutine? And it turns out that you can do this. You will probably pay a big penalty in code review, but if you are willing to do, what's known as frame hacking, this is like evil. There's the get frame function, if people might know about that, where you can look at the call frame of your call, like the person who called you. You can actually go up and determine whether you have been triggered from a coroutine or not. So what I've got here is I have a normal function foo, and it's basically going to say, hey, have I been called from a coroutine? If I call that, it will come back saying, no, you haven't. Down here, I have this async main, and I use this thing saying, have you been called from a coroutine or not? If I run that, it will come back saying, yes, actually, you have been called from a coroutine. And you could say, where is that going? Well, it turns out that this opens up some really interesting things if you're willing to get into things like decorators, right? So you can write, you can start writing decorators that wrap functions and maybe start enforcing rules. What is going on here is this is a decorator that basically tags a function as saying, you cannot be called from coroutines. Like this spam, it says sync only. If you call it from interactive, it will come back saying, okay, that's cool. You're not in coroutines, but if you try to run it from this like coroutine stuff, it's going to crash saying, no, I'm sorry. One of the reasons why you might think about that, by the way, we'll get to this, is one issue with a lot of coroutines concerns the behavior of blocking operations. Turns out if you're doing event loops and you do some operation that blocks the event loop, the whole thing shuts down. It causes lots of performance problems. Potentially, you could use something like that to lock it off, right? I mean, you could say, look, this function is not safe in coroutines. You could tag it, and it will not be called in coroutines. Now, you're going to have to explain to the Python gods why you're using a frame hack for this, and that's a whole different issue, but you can do that. Some other possibility, this is kind of an even more insidious thing. Maybe you could have the same function name, but do different things depending on whether you're in coroutines or not. So what I've got here is I have a function spam, which normally says, if you call that, it comes up and says, oh, you're the blue pill, because that's like a normal function. But then there's like this weird awaitable version of it that if I call that from like a coroutine, like I say await spam, it comes up and says, well, you're the red pill. I don't know whether this is like completely insane or not, to have like the same function, like you have a function spam that works one way in one context, but another way in a different context. I see more cringing up in the front here, so it's fun stuff. It gets better than this, by the way. There is something known as asynchronous iteration. Like asynchronous iteration, what is that? Well, what you can do is you can write iterators, like you can say this is something called a countdown, and you can do what's known as an async for loop. An async for loop. I was like, what is that? Essentially what this is doing is it's giving the iteration protocol an option to call coroutines. Like you can call other coroutines in the next in the iter method. Again, to run that, okay, so I messed it up. I'm not gonna type it in again, just in the interest of time, but you can do asynchronous iteration there. There's also an asynchronous with statement. Like you can have like a context manager that uses a enter and a exit. I mean, what this is about is you can make a manager, I'll just call it M. Like that, and then you use an async with statement. Hopefully this will work. Okay, I've redeemed myself a little bit there. Okay, so you're looking at this. I mean, so first of all, I guess I mean the question. Okay, we're kind of scoping out a little bit the space of these async functions. Okay, you have these async functions. They can be used in a lot of different ways. Like they can be used as methods, functions, some special methods. There's things like asynchronous iteration, and so forth. And you can, I guess maybe the question that comes up is like, why? Like, why are we going into all, like, what is going on here other than just creating like this insane, weird world? So in thinking about the why, one possibility might be this. You want your coworkers to hate you. I don't know, I found this quote online. This blog, by the way, there's this blog, What Color is Your Function? It's actually an excellent post, by the way, that talks a little bit about what we've just been doing here. It talks about this idea of blue functions and red functions, and some are async and so forth. So I would definitely recommend reading that. But I think that the bigger picture of why is really this. Going back to like a lot of this network code, this I/O code, let's say you have some function like receive on a socket. Why do you care about that? Well, let's talk about this for a second. If you do an operation like that, it's ultimately going to involve some kind of system call. It goes down into like the C library and does a system call somewhere. If it's making a system call, at some point it's going to talk with the operating system kernel. And then the operating system kernel is just going to block everything because you're waiting on a network interface for some packet to show up. Okay, so you do an operation like I/O, it's going to go down into the system and it's going to block. Okay, so this blocking, this is really the whole point of everything, because this is why people are using threads and processes. I mean, this is the thing that prevents concurrency, is the fact that your Python program blocks and then everything is like shut down. So you end up with this problem of how do you get around that? That is the problem, the ultimate problem. Now, kind of riffing on this figure a little bit more, one of the things that you might know about systems is that there is a fairly strict separation between the two spaces that you're operating on here. Kind of up at the top, this is the world of Python and C programs and applications. You have user space, and then down below you have kernel space, which is, that's the operating system and so forth. One thing about that kernel space, you never see that as far as a user. Like, if you're up in user land, you're not really looking into the kernel. You might also know that getting into that kernel space usually involves a special operation, either a trap or an interrupt or something. It has to do with getting you into protected memory mode and other things. So there's essentially these two spaces that are existing. There's a way of getting from one to the other. And the reason that I'm talking about this is that this async stuff that we're doing is kind of the same. You have async space and you have normal space, if you will, or synchronous space. And what's going on is that when you're working with async functions like this, async and await, you're kind of up in this world of, async function. And so up there, you have your code like that. This kernel space, in some sense, is kind of like that run function. Keep in mind that coroutines never run themselves. They're always running under the supervision of somebody else. It's kind of what kernels do, like in an operating system. It's like they're running code, they're supervising your code. So this model from like an operating system where you have like user space and kernel space, maybe that's kind of what we have going on here. We have async space and we have synchronous space. The question, though, is what sits in between? There has to be a way of getting from one to the other. And this is really kind of the magic trick. The way, or the bridge between those two worlds, is through Python generator function. That's why that involves like a stop iteration and other things. So somewhere in the system, there is something that gets defined with the yield statement. That is basically the magic that makes this whole thing work. And the reason that is the magic is, well, let's talk about that. The reason that works is the essential feature of yield is that it causes your function to basically stop. Like if I do that, like let me just try this out here. Okay, let's say I'm going to import types, and let's say we do types coroutine. I have a typo on that slide, by the way, so forgive me. Okay, so let's say you had that, and let's say you had a yield in here, like that. let's say I were to have some function that called that somehow. Like, let's say I had an async function. We have async main like that. And I just said, like, await a read. Like, await read, I don't know, 3/1000. So, something like that. And then what I'm going to do is revise the run function just slightly here. One of the things that I want to do on it is actually just print out what got yielded on this thing. Because this is kind of the same run function as we had before. What's going to happen is if I run that main, what will happen is it will run, but it will hit the yield statement and it'll just sort of stop. It'll just say, well, you yielded read. And now we're back at the prompt. It's like the coroutine ran and it sort of stopped midstream. So you have this magic trick. It causes coroutines to stop. And the reason that people care is that is the mechanism for getting this concurrency to work. It's the way that people get this cooperative multitasking to happen is through that yield statement. That is what is driving it. And having seen that, I'm going to pose this question. Should you even care about this? I mean, do you care? Like, should you care? And I've given a lot of talks about generators and coroutines and things over the years. I mean, I gave this kind of famous coroutine tutorial and so forth. I'm looking at this async stuff. I'm looking at that tutorial, and I'm thinking, should I care at all about that tutorial at this point? And I'm not sure that I should. Maybe as an analogy, do you care how a system call works on Linux? I mean, how many people in here have actually cared how a system call works on Linux? I mean, unless you're writing like an operating system. I mean, like me as a C programmer or a Python programmer, I do not care how that works. Like, I mean, yes, it loads registers and it does a trap and so forth, but I have never once had to think about that, ever, like in writing an application. And I sort of wonder, like, if you're going to go into this magic world of async and await, do I ever have to care at all, ever, about this facet of it? Yield, generators, I don't know. The reason why I bring this up is I want to talk about some of this other async stuff. Is there any reason for me to ever care about event loops or callbacks or futures or transports or protocols or any of that stuff? More specifically, do I need to worry about what is going on in the async IO library? Have people looked at async IO? It's a new library, showed up in Python 3.4. It's been around a little while. If you look in there, there is a lot of stuff going on. I mean, we could do the help on it. It's going to be nasty because it's auto-generated, but it's got like coroutines and event loops and queues and transports and protocols and tasks and futures and all of this stuff. And I guess my question is, do I care? Do I want to care about that? And I'm not sure that I do. And so when we get into the last part of this talk, it's really this question. Can I program async and ignore all of that? Can I ignore everything in async IO the same way that I can ignore how a system call works on Linux? Like, can I stay at a high level? Maybe another way of thinking about this is, can you flip the narrative on async a little bit? Specifically, this is what is, if you go back and you watch like Guido's talk on async IO and things like that, one of the things that they talk about in there is this idea of having an interoperable event loop. Like, can you have these different libraries like Twisted and Tornado and G-Event and so forth? Can they operate on the same event loop? Essentially, the problem is, if you're working on one of these async libraries, they have to have an event loop. And you can't have like 3 different event loops running. That's the problem. And so there's this idea of an interoperable event loop. Can you flip this whole thing to do this? This is kind of what I'm thinking about. It's like, instead of the interoperable event loop, could you have like an interoperable API doing async and await? And if you did, could you run your code on just whatever event loop that you wanted without worrying about it? Kind of the same way that I could take like a C program and run it on Windows and run it on Linux, as long as they both have like POSIX functions or something. You know, it's the same kind of kind of idea. So this is something that I've been kind of playing around with in a project for the last 8 months. I don't necessarily want this to be a plug for this project, but I've been working on this Curio library, which is in some sense, it's like an experiment in seeing whether you could just go all coroutine. In fact, you've actually already seen the main interface to this library. It provides one function that is normal, which is the run function, and that is basically it. Okay, so you can write async functions, and you can run them. That is actually the only part of this library that does not work out, that works outside of coroutines. The entire rest of the library is pulled completely into coroutines, trying to do absolutely everything in the coroutine universe. Turns out that this code that I had earlier, that was running on Curio, like this async server kind of code that we had earlier. There are simpler versions of that you can simplify. This is also Curio code. It looks very similar to things that you might write with threads and so forth. And part of I guess kind of the experiment of trying to do this. Okay, so you know, I sometimes ask myself like, okay, why in the hell am I writing an async library? I mean, it'd be like I'm going to rewrite Emacs or something. I mean, there's already a lot of like, you know, async libraries out there. I guess part of the experiment is just to see what it looks like to program all in coroutines, like just to see if this can even work at all without your head just shattering, basically. Okay, so part of the experiment is that. Part of it is just to see, like, does it have performance? I mean, like, is this even a good idea or anything? So I thought I would talk about just a couple of like facets of it that have come up. One of the ways that this library operates, by the way, is it tends to put wrappers around things. What you tend to do is you use ordinary objects like files and sockets and so forth, and then what you end up doing is you replace them with like wrappers that go around it. Essentially, the purpose of these wrappers is to do asynchronous stuff. So like what I've got here is I've opened up a pipe to some command using the subprocess module. I've taken the two files on that and put like a wrapper around it, like this standard in, comes back. It looks like a file object, but if you try to do anything on it, it will come back with coroutine. Everything is a coroutine. Okay, so if you want to do anything at all, you have to stay in the coroutine world. Okay, so you can run that. One of the things that have found in doing this is that a lot of the programming actually does read in a fairly straightforward way. I mean, this is something that communicates with that subprocess. Just kind of talk about what it does. It's spawning a task to read all the data off of standard out. Then it's doing a timeout, then it's writing data and then collecting data off of a task. It's a short amount of code. It's something that can often be understood. Another thing that has kind of come out of this project is that the performance of it has been way more than what I would expected. This is an example of some benchmarks with this Curio project, just putting it up against some different frameworks, including gEvent and Twisted and Async IO. What we're doing here is it's like a 16-core Linux server. It's got a bunch of tasks, just like hammering the server as fast as possible and seeing how fast it goes. It's not bad. Almost 50,000 messages a second on this like Curio async only like coroutine thing. We're up above gEvent. gEvent uses a C extension. Okay, so I mean it's kind of, I mean, I'm kind of shocked, to be honest. One thing that is new, by the way, there's this project UV loop, which is a async IO. It's a re-implementation of the async IO event loop using libuv, which I think is used by Node. And definitely not as fast as that if you want to stick in callback functions, but if you're doing coroutines, this Curio project is still pretty fast. So some interesting things there. But I don't really want this to be like a curio talk per se. What I really want to talk about, we're getting near the end, is I want to go back to this code. Okay, so this is this async await code that was used in the curio example. And I guess the question I would pose on that is, where are the dependencies on a library in that code? Like twisted or async IO or like import statements. Where are the import statements in that code? What I have is an async function. It's using await. It's not really using anything else. And I guess the thought that I have about this is that couldn't that code run on a whole bunch of different things? Like couldn't, again, this interoperability, could that exist at the async await instead of the event loop? It doesn't matter who runs that code. Does it matter that it runs in Curio? Does it matter that it runs in async IO? I don't know. Do the details matter at all? I think that you could actually probably adapt that to make it run on async IO. It's an interesting idea. People have done this sort of thing in Python before with things like Whiskey, the database API, things like that, common APIs. Why couldn't we have something with async await? It's an interesting idea. So those are the thoughts. Now the challenge is, if you're going to do this, we're getting near the end. I think I have 5 minutes left? Okay. So let's say you wanted to do this. I think the first challenge is just, is this async await stuff even a good idea to begin with? I'm not so sure after the earlier discussion of the asynchronous meta classes, and so I saw some cringing and scared looks, but the part of the point of doing that was just to kind of scope out the whole world of that async await and what's possible. You have this whole world of stuff. Is that sane or not? I don't know. Okay, I honestly don't know. So that's one challenge. The other challenge, if you're going to do it, is just what makes a good API in this async world. Having experimented with this, there are all sorts of holes that one can fall into that are very scary. I'll give you an example. One debate that I've had in the Curio project is whether to make close an async method or not. One argument is that, well, close doesn't really do anything, so just make it normal. But then you get these other cases like, well, it could be a file, and maybe the file is buffering up a bunch of data, and then when you close it, it has to flush the buffer out somewhere. But when it flushes the buffer out somewhere, it could block, because, blocking IO, and then the close method blocks, and then your whole event loop is stalled. Okay, so that maybe you should make it async. But then you can make an argument, it's well, maybe it should just be async on files, but not on sockets. Well, that's crazy, because then it's synchronous in one place, but not in the other. So you have no consistency, right? So it's lots of tricky stuff there. Another tricky part is, I think if you're going to do this, you have to keep the event loop out of it. One complaint that I have with async IO is that it requires the event loop to be carried around everywhere. If you use that library, you'll find it kind of everywhere. I don't think you need it. When you're working with coroutines, you know who's running the code. Whoever's running the code is running the code. It knows what the loop is. You can simplify it. The other challenge is, I think you have to go all in. If you're going to do I/O, it's everywhere. It's sockets, it's files, it's directories, pipes, subprocesses, timers, the whole universe. Anything that blocks is going to destroy your event loop. I was actually talking with somebody recently. They were talking about it at work. They're rewriting a Python project in Go. I'm sure that nobody has heard this recently, right? It's rewriting Python in Go. And I say, well, why are they doing that? Well, they're using G-event, but there's some kind of weird performance problem. And I was like, oh, what's the performance problem? They're like, well, under load, the thing gets really slow. And it's so ended up digging a little bit deeper. And okay, so they're using G-event. But then what they were doing is normal file I/O, just with the open function in the code. I mean, if you know about files, it's okay, you open up a file, I mean, that can go out and hit disk. I mean, it's we're talking rotating platters or, whatever. And it's your whole universe grinds to a halt for 5 milliseconds or something. And they're wondering why the thing is slow. It has nothing to do with G-event. It has everything to do with the fact that they're doing this stupid synchronous I/O operation in the middle of it. So if you're going to do this, you have to go all in, however that's going to work. Okay, I already did that one. Okay, so as far as closing this thing off, I think there are some opportunities here. If you're looking for just a cool, insane thing to be working on, async await is where it's at, I think. I mean, there is a lot of like weird stuff. First of all, you'll shatter the heads of all your coworkers. They're going to look at your code and they're just be like, what is that? You can also forget about any version of Python prior to 3.5. So forget about porting or backporting, or it's like, no. Okay, so you don't have to do that. The other thing I thought I would plug here, you have to look at what's going on in the protocol world. This is Corey Benfield's work doing HTTP2. One of his things that he's been promoting is that I/O protocols should be decoupled from I/O. And he has this HyperH2 library, which implements HTTP2. That library is totally agnostic on the I/O model, like whether you're using threads or async. I've used it with Curio. It is a really cool project. You should definitely check out his PyCon talk, because it is it is sort of in this same space of like, where do you draw the line on implementing some of this stuff? So that is basically it. The end of the talk. I don't really have any final comments other than, this async await stuff. It's a very odd, strange universe in Python. If you're looking for something fun to work on, get involved with it. So I think that's it. I just got the 0 minutes, so they're going to kick me off here. So thank you very much. Hope you're welcome.